lesson is pH of bases.
Okay, very good. Thanks, Anna.
Is that all you?
In our previous lesson, we looked at the pH of acids. Now we're going to look at pH of bases. We're going to look at strong bases and weak bases. We're going to treat these just like we did with the strong acids and the weak acids. With strong acids, we didn't have to worry about equilibrium. But when we had a weak acid, we did worry about equilibrium. The same thing here. Strong bases, the 6 ones that you were supposed to memorize, are not going to require any sort of Ka or any Kb in this case. So that would be NaOH, lithium hydroxide, potassium hydroxide. These would be your strong acids that will not require equilibrium. Calcium hydroxide, barium hydroxide, and strontium hydroxide. So anytime you have any of these acids, all you're going to do is you're going to take whatever the concentration is of the base. I think I said acid there. Whatever the concentration is of the strong base will be the concentration of your your hydroxide. Okay, because keep in mind with strong bases, what you're going to do is you have something like sodium hydroxide. What it does is it breaks down completely into sodium and hydroxide ions. And that's one of the things students have the most difficulty with bases, is they forget that they're dealing with hydroxides and they kind of just take the negative log of hydroxide and think that's the answer. But remember, if you take the concentration of hydroxide, you're going to get POH. So you got to figure out what the pH is. So be careful with that. I'll show you an example of that. So whatever the concentration of this is will be equal to the concentration of hydroxide, because this reaction shifts completely about 100% to the right, towards the product side. Okay? The ones you got to watch out for are the weak ones. And these are the ones that notoriously throw students for a loop because you're not used to seeing organic molecules. The biggest and most common weak base you're going to see is ammonia. Okay? Ammonia is the one you see quite often. But it's not just ammonia that you're going to be looking for. You're going to be looking for ammonia groups or ammonia structures. And in organic chemistry, what you can do is you can take a hydrocarbon. So let's say you have something like carbon with 4 hydrogens around it. Okay, you got hydrogen here and here and here. So this would be methane. What you can do is you can actually chop off one of those hydrogens, and if you stick on here what's called an amine group, which would be a nitrogen with 2 hydrogens on it, what you end up with is a methylamine. This is what's referred to as an amine group. So you have the methane, methyl, and then amine. Now don't worry about the organic naming and all of that right now, but what you want to look for is this structure right here. This is the structure that's going to make your organic molecule basic. Okay, this is an organic base. On the AP test, they do tend to give these to you, but they will give you the name and they will tell you it's a base. The other reason you're going to know it's a base is most likely they'll give you the reaction and you'll see the formation of hydroxide. The other thing that they're going to tell you is they're going to tell you what the Kb is. So there's ways of kind of seeing through the nonsense, but students just kind of forget and don't really get what to do with these particular structures. When in doubt, and when you're trying to write the equation, when in doubt, just always remember what a base does. Bases draw in or attract hydrogen ions. That's their function, right? That's what they will do. So what I would do is I'd rewrite water as HOH, and I would treat the base. How do I know it's a base? Because it's got the nitrogen and hydrogens in it. And I would take that hydrogen and put it with this, and that's why we get H plus added to this molecule. And then we're left behind with the hydroxide. So when in doubt, just always go back to what does a base do? If you're trying to write the reaction here, what do bases do? They take in hydrogens, they attract them, they bind them, they pull them into their structure. Okay? Alright, so let's take a look at other types of bases. So you have the strong bases, which are the ones I listed before. You have the weak base, ammonia, and then its groups, that's in the organic molecules. Then you have conjugate bases of weak acids. All right, so if you have hydrofluoric acid, okay, and you react that with water, H2O, what it does is it makes H3O plus, and this is equilibrium here, and it leaves behind a fluoride ion. Well, if you remember the conjugate stuff we talked about, this is your acid, this is your base, this is your conjugate acid, well, this is a conjugate base. Now, if this is considered a weak acid, what that means is it doesn't lose the hydrogen ion that much, right? It doesn't readily lose the hydrogen ion. So what that means is that fluoride must be very good at pulling the ions. So fluoride, if you think about it, fluoride has a negative charge on it. Okay, and what that means is that if there's a hydrogen here, it's going to attract it. It's going to take that hydrogen ion directly from it and bind it and create a hydrofluoric, acid molecule, okay, or a hydrogen fluoride ion, okay, or I'm sorry, molecule. So what we find is that if I have this in a different form now, okay, let's say that I don't have hydrogen fluoride, but I have something like sodium fluoride, right? You should know from solubility that the sodiums are always soluble, so this will dissolve and dissociate into ions. So how does this actually exist? It exists as two ions. Well, if this is aqueous, right, because it's dissolving, that means that water has to be there. So therefore we have sodium ions. Okay, these are my species that would be present. And I would have fluoride ions, and I would have water. So what happens here is that these two ions, or this ion here, is going to react with the water. And that's the reaction that you see here. Okay, so your conjugate bases from weak acids are considered bases. They're considered weak bases, and they're going to react just like they do, any other base. It's going to take the hydrogen, so I would rewrite the water as HOH and give it the hydrogen ion, because that's what a base does. It takes that hydrogen ion. Why is this happening? It's based on the equilibrium. Where does this reaction favor? What is it? Does it favor the reactants or does it favor the products? Well, Ka for these are very, very low. I think this is like 7.2 times 10 to the minus 4. So therefore, it favors the reactants. So therefore, fluoride shouldn't be existing by itself as an ion. It's going to bind really quickly with that hydrogen. Unlike HCl. HCl is a strong acid, so H plus and Cl minus, what happens is the reason why this reaction goes so far to the right is that chloride has no affinity for that hydrogen ion. It's not going to attract that hydrogen ion at all. In fact, the water is going to attract it way more than the chloride would, and that's what makes this such a really, really, really bad base. It's a very negligible base. So chloride will not react with water. So you're not going to get this reaction here for this to make, HCl and OH minus. This reaction does not happen because chloride is a very very weak base. So weak we don't even acknowledge it as a base. All right. So what that leads us with is, I guess I better hurry up. What that means is we're going to have the pH of weak bases, and that's going to give us the same thing we did with our acids. We're going to write the equilibrium expression where B is any of the weak base. So B could be ammonia, B could be fluoride, nitrite, any of the ions. This is really important to focus on this. These are ions that are, it's not nitrate, it's not sulfate and all that kind of stuff. These are the ions that are coming from weak acids, not from the strong ones. So we would have cyanide would be in here, and H2S, stuff like that. Those are all going to be considered bases. So that I could replace that B with any of these things here. All right, so then we would write the expression Kb, and that would be my base dissociation constant. Remember, what does the base do? It takes the hydrogen ion. So whatever my original base is, I add a hydrogen ion. It's left behind with a hydroxide. Keep in mind, this is different from the weak acid ones. With a Kb, what you're looking for here is the hydroxide. So you're going to have hydroxide, not hydrogen ions. And get this a lot. Students miss this part, and I'll show you an example in just a second. And just like before, the higher Kb is, the more the reaction lies to the right. So if Kb is larger and larger and larger for different bases, then we have higher and higher, concentrations of ions, therefore making it more and more and more basic. Okay, so the higher the Ka, the stronger the base. Why? Because we'll pull the hydrogen with a greater force. Okay, so it all comes down to understanding that basic general idea. Okay, so let me show you how to do this calculation of the pH of ammonia, quarter molar. Dissociation expression, which would be the reaction of the ammonia with water. Again, HOH. What it leaves behind is ammonia with a hydrogen ion, which now becomes ammonium. And I also have a hydroxide left over. All right, so I'm going to start here with the ice table, ICE. Water is a liquid. We don't care about that. I'm going to put 0.25 molar here, 0, 0, plus x. I'm sorry, not plus x, but here it's going to be minus x. Here it's going to be plus x, plus x. And notice the pattern. Pattern is going to be the same general pattern we saw with the weak acids, which is nice, but it also can lead you to make a very, very common mistake, which I kind of already alluded to. Now, I've told you before to write the expression, which would be the Kb this time, and we're going to write the products over the reactants. Take the time to write this step. Remind yourself that you are not dealing with hydrogen ions, but you are dealing with hydroxide ions. As I said before, students that skip these steps tend to make more mistakes than those that put this step in. So now I substitute in x squared over 0.25 molar. I'm going to get rid of that x because the Kb is so small. It's such a small Kb I can drop it out. So 1.8 times 10 to the minus fifth. I can solve for my x, which is equal to the concentration of hydroxide, which is also equal to the ammonium, which I'm not really concerned about. And when I do that calculation, I end up with 2.12 times 10 to the minus third molar. Alright, so that is the concentration of the hydroxide ion. I can find the pOH of this by taking the negative log of my hydroxide concentration. And if you want, you could find the hydrogen concentration and then take the negative log of the pH. But I tend to like to do it this way. 2.67. And then to find my pH, I just do 14 minus 2.67. And that would give me 11.33. And there is my pH of a weak acid, in this case the ammonia, at a quarter molar. Now, what does this mean? Think about this. Not only what does it mean, but just check your work. Think about this. If the pH is 11.3, does that make sense that it's a base? Yeah, because if its pH is greater than 7, then we know that we have a base, and that's what we want. We want the pH to be greater. A lot of students do this as the pH calculation because they don't bother. They just keep x, and then they just circle this as their final answer. You should know that's wrong, because if it's a base, the pH should not be that low. It should be very high because pH higher than 7 is a base. Alright, so that's generally it. I mean, it really is not that much different than the weak acid problem. It's that the strategy is all the same thing we did in the last chapter as well, in the previous unit. So really, just the basic strategy is there. Just watch for the little nuances and just be careful of what you're doing with the base. Alright, I'll take questions in class, and I'll see you later, guys.